Have you ever wondered if the universe has, an instruction manual? Well, it does. And for centuries, we've been piecing it together. We call it physics. And trust me, it's not just for some stuffy classroom. It's literally the code that explains everything, from why your phone drops to how a jumbo jet stays in the air. So, let's crack it open. All right, let's just dive right into the biggest question of all. How does any of this work? I mean, it seems impossibly complicated, right? But the most amazing part is that it all boils down to just a few surprisingly simple and kind of elegant rules. And today, we're going to build that rulebook piece by piece together. Okay, so first things first, we need to learn the language. You can't read a book if you don't know the alphabet, right? Well, you can't understand the universe's rules without its basic vocabulary. These are the fundamental ideas we use to measure and describe reality itself. And this is where it all starts. Just look at this list. Absolutely everything in the universe, from a giant star to a tiny speck of dust, can be described using combinations of just these 7 things. Think of them as the atoms of measurement. They're the absolute foundation that everything else is built on. So from those basic building blocks, we create 2 main types of measurements. The first one is called a scalar. Just think of it as the simple stuff. It only tells you how much. How long did it take? What's the temperature outside? It's just a number, a single piece of information. But sometimes how much isn't the whole story. We also need to know which way. And that's where a vector comes in. A vector gives you both things, the magnitude and the direction. It doesn't just tell you how fast you're going, it tells you where you're headed. See? This slide nails the difference. Your car speedometer says 50 kilometers per hour. That's a scalar. But telling your map app that you're going 50 kilometers per hour north, now that's a vector. And believe me, that one extra piece of information, the direction, is absolutely critical in physics. So now that we've got our vocabulary down, scalars and vectors, we can start describing one of the most basic things in the entire universe, motion. We can literally draw a map of an object's journey through space and time. Okay, I know, graphs can look a little intense, but they're just telling a story. On the left, we're tracking where something is over time. See that flat red line? That just means it's not moving. It's staying put. Now look at that sloped line. That means it's moving at a nice, steady speed. And the cool part? How steep that line is? That's its speed, its velocity. So when we graph its velocity on the right, that steady speed just turns into a simple flat line. See? They're just 2 different ways of telling the exact same story. Now let's try something a little more complex, like throwing a ball. It looks like one complicated arc, doesn't it? But physics lets us peek behind the curtain and see what's really going on. It's just 2 simple motions happening at the exact same time. The ball is moving forward at a steady clip, while gravity is pulling it down. The rulebook takes something that looks complex and makes it simple. Okay, so we're getting pretty good at describing how things move. But what about the why? What makes something start moving in the first place? Or stop? Or turn a corner? Well, to answer that, we need to talk about the main event. Force. The definition is so simple, but it is incredibly powerful. A force is just a push or a pull. That's it. If an object's motion is changing, you can bet a force is the reason why. No exceptions. It's the engine that drives all change in the universe. And the rules for how all forces work were laid out for us by Isaac Newton in his 3 famous laws. These 3 simple ideas govern everything from planets orbiting the sun to a game of billiards. First, inertia. Basically, objects are lazy. They want to keep doing whatever they're already doing. Second, acceleration. If you want to change an object's motion, the force you need depends on how heavy it is. And third, action-reaction. You can't push on something without it pushing back on you just as hard. Let's look at a force that you are experiencing right now. Why are you falling through your chair and through the floor? It's because the chair is pushing back up on you. Physicists call this the normal force. It's a perfect real-world example of Newton's 3rd law. Your body pushes down, the chair pushes right back up. Simple as that. And here's another one we deal with every single day, friction. You can think of it as the ultimate opposing force. Anytime you try to slide something, friction is that invisible force that pushes back, resisting the change. It's the reason you have to keep pushing a heavy box to get it to slide across the floor. Now, talking about forces is a great way to understand the universe. But there's an even deeper, more fundamental level. We can reframe the whole thing not as pushes and pulls, but as transactions in a kind of universal accounting system. And that system is called energy. This right here is one of the biggest, most important rules in the entire rule book, the law of conservation of energy. It basically means the total amount of energy in the universe is fixed. It was set at the Big Bang, and it has not changed one bit since then. All it does is change form. This is the perfect way to picture it. Think about a roller coaster. When it's way up at the top of a hill, it's moving pretty slow, but it's loaded with stored energy just because of its height. We call this potential energy. Then, as it screams down the hill, it trades that height for speed, converting all that potential energy into the energy of motion, which we call kinetic energy. So here's the key takeaway. The total amount of energy, what we call mechanical energy, which is just the potential and the kinetic added together, it stays the same. The amounts might shift back and forth, more potential at the top, more kinetic at the bottom, but the total balance is always, always conserved. Okay, let's take a quick pause. We've learned the language, we've described motion, we've understood forces, and we've gotten a glimpse into the universal bank account of energy. Now, with this rulebook in our hands, we can start to unlock the secrets behind some really complex, real-world stuff. Let's start with hydraulics. Have you ever wondered how a tiny push on your brake pedal can stop a 2-ton car? Well, the answer is something called Pascal's principle. It turns out, our rules of force, when you apply them to a liquid, show that pressure gets transmitted equally everywhere. This means a small force on a small area creates enough pressure to make a huge force on a bigger area. It's basically a force multiplier. Or how about flying? How does a giant metal tube stay up in the sky? This is all about energy and pressure. An airplane wing is specially shaped to make the air travel faster over the top of it than underneath it. And our rulebook tells us that faster moving air creates lower pressure. So what do you get? High pressure under the wing pushing up, low pressure on top. And that difference? That's lift. See? These rules are everywhere. Even something as basic as heat is just energy on the move. And it always moves from hot to cold in 3 very predictable ways. You've got conduction. That's heat transfer from direct touch, like the pan getting hot. There's convection, where heat is carried by moving liquid or gas, like the water circulating. And finally, radiation, which is heat traveling as invisible waves, like the warmth you feel from the flames themselves. So as you can see, from a falling apple to a flying jet, it all comes back to the same core set of rules. Physics isn't just about explaining the world as we see it, it's the toolkit we use to design the world of tomorrow. The rulebook is in our hands now, so the only question left is, what are we going to build with it?